Okay, so some people ask us about our scaling capability at Automedi. And it's a difficult one to answer without explaining how typical scale is thought about within the health service, and in fact in most manufacturing capacities more generally. Because manufacturing doesn't stand alone in any sector. There's actually several things that happen from the point at which something is manufactured, which is here, all the way to the point of its use, which is here, and then into its, I'll call it final destination in terms of disposal, which is here. The difficulty you have is that it's a system. And as I say a lot, you've got to think about everything as a system and how to optimize that system. Let's visit how conventional supplies are supplied to the health service and indeed to any other sector typically, especially when it comes down to the consumer sectors. The first thing we, of course, start with is some manufacturing of some sort. Into here comes some raw materials of some kind. Now, that may very well be plastics, processed plastics, obviously, which are derived from oil or something else. And that doesn't come in with zero footprint. So from the perspective of looking at the carbon capacity, if you like, that's already locked in, there might be some amount, call it X. Each factory actually emits between 1 to 10 consumes gigawatt hours of energy. Now that's a substantial amount because typically, even from the cleanest sources, it has around about 40 grams of CO2 from the cleanest sources. This is per kilowatt hour, sorry. But actually, sometimes it's a lot more than that. It's not uncommon for this to be well in the region of 400 to 1.2 kilograms per kilowatt hour. That's a lot of CO2 that's emitted, I'm sorry. So you can totally see that these numbers are quite significant. And that's because of the way manufacturing is actually done. It's not just the machines that need powering, it's also the building itself. And the net result of that is significant energy consumption, just in heating. Never mind the actual manufacture. Now, a lot of the machines are designed to run very quickly and produce millions of items, but the trade-off with that is that those items are created on three-phase power supplies, which typically have no less than 4,800 watts of power delivered via them. Now, that's significantly more than a typical home environment. And this is obviously a big issue because each one of those machines is dragging all of that. So there's very significant amounts of power that are going into this thing, which generate very significant amounts of CO2, as can be seen here. Now, even if you've now manufactured lots and lots of stuff, the other thing you've got to do is to take it from the factory through haulage to a ferry terminal or some other freight terminal. That gets shipped around the world or flown around the world across some national boundary usually. And that distance here could be thousands of miles. Once it lands, obviously there's customs processes which can include a bit of a stay for the load itself. And then it's hauled to some storage facility until it's needed, in which case it's then distributed through the logistics chains, and there's multiple ones of these, to wherever it's needed. It might be some pharmacy in some part of the UK or any other nation. It might be straight to the hospital, GP surgery with other pharmacies attached, or whatever. The items are then used as required and either given out to the community via a pharmacy or GPs. So this might be Joe Blogs, you and I. Or it is used within that context and then disposed of. So one example may very well be that you'll give inhalers under a prescription to Joe Blogs here. And at the same time, you may very well be delivering dossets or pill trays within a pharmacy, which you'll usually decant medicines from a pot or other blister packs. And that then goes straight into waste. What this then does is accumulate not just the waste in this space, which remember has come from the manufacturing process itself, but it also accumulates more carbon dioxide collecting and disposing of it. And it's not uncommon for most bin trucks to travel only 8 miles to the gallon, which is a ridiculously small distance. Now, the good news is there are some bin trucks that are electric nowadays. We've got one not a million miles from where we are in South Manchester. So And that's good news because, of course, then that significantly reduces the footprint overall, reduces cost, which is great for them too. But, of course, if it doesn't come from a green source, it still has an impact. And even if it does come from a green source, the impact is minimal. And there's two places where this waste can go. If it's medical waste, it has to be incinerated. Now, that is extremely expensive. It's not uncommon for that to cost around about, let's go and pick a colour for explaining the cost, £3,000 per tonne just to incinerate it. Never mind the transit costs from this process or this process. Or it can end up in landfill. And landfill, of course, comes with a tax associated with it, around about £76 or so per tonne for a landfill tax in any one area. So there's a cost associated with that. And of course, that is passed on to the pharmacists and GPs via the CCGs effectively. So that is effectively a typical supply chain. Very, very linear. Starts with the manufacturing of something from some raw material. Goes all the way through the chain, accumulating carbon in every single one of these steps, and quite significant amounts as well, only to then be dumped in landfill or incinerated, which releases the carbon dioxide stored within each element. And it's not uncommon that the incineration step alone emits about 45% of the weight of the waste in carbon dioxide. So that's obviously unsatisfactory. And the reason for that is because when you start to account for the amount of carbon accumulated here, so I'll use our little blue arrows, the total amount of carbon dioxide embedded or embodied within each product which is embedded in the supply chain is a total of 300 to 1,000% of the weight of an item. So every time you buy an item, that's effectively the total carbon dioxide that you've emitted creating it. Now let's talk a little bit about the scale problem. So in traditional conventional manufacturing, people think about scale as if you're a manufacturer, you have to create or you have to be able to deliver more items from one factory. But there's a couple of problems with this style of thinking. This is what's known as vertical scaling, because what you're effectively doing is scaling the ability of the one factory to do more. For example, it may very well, or your service to do more. And that might very well be making machines run faster, getting a couple of machines within the same factory. And all of those creates a series of constraints downstream of it. So let's suppose that you have, let's go and look at this from a blue line. So let's suppose, let's go back line. Let's suppose you generate, for the sake of arguments, 1,000 items per minute. And that will fill one lorry's worth in, say, an hour, right? Lorry in 1 hour, right? Okay, so that means that typically 60,000 items, 1,000 items go into one lorry, straightforward enough. And then the freight or container freight ship might very well take, let's say for the sake of simplicity, we'll say it takes 300 containers, 300 lorry loads, basically. Loads, there we go. Other side, that means that 300 lorries will suddenly appear here to take everything from the freight ship through to its various storage locations, wherever in the country they may reside. Okay. And then, of course, each of those has a set of logistics, and that takes it to their own individual locations within primary or acute care, and they get used as required. So let's now imagine we are able to get one lorry load going out every single day at the moment. As soon as we want to scale the system, let's say we double it. We want to provide 2,000 items per minute, effectively, to then deliver the demand required here. What does that actually mean in real terms? People think, okay, well, you just scale the factory, you can deliver this much. And that's often how procurement and commissioning think about it. It's just, you're giving us double this amount. But in fact, it's a complex chain of a number of different things that have to be organized all the way through to the point at which it will be used. So let's suppose we double the capacity of the factory. Now we also have to double the number of lorries that turn up. But this leaves us with an interesting issue. Because the haulier isn't necessarily reserved for this particular manufacturer. In fact, they might have multiple manufacturers. So let's now require 2,000 items per minute. But if we are unable to get more than 2 lorries, you have now got a backlog of stuff that's sitting on the outside edge of that factory. Because you're still delivering it through 1 lorry instead of the 2 lorries that you actually need, because the haulier might not be able to deliver that chain, that capacity. Once you've done that, you've then got the question of how you get it on the container ship. Because if the container ship is full already, you have no space for your elements, and in any event, as soon as you go on it with your extra capacity here, you effectively have to take 1 item off that existing freight ship from potentially someone else. So you have to control that chain, but in reality, most manufacturers in the UK do not, and anybody that's dropped anything on the market does not, because they don't control those elements. This is actually a freight system. It's independent of them. So unless they buy their own tanker, container ship, they're not, realistically speaking, going to be able to control that part of the process. Regardless of what happens, your 1 freight ship is still going to have exactly the same capacity here. So that means that, let's suppose there are 300 containers on this freight ship, and there are no extra freight ships making their way to the shores of the UK, for example, then whatever happens, you are still stuck with only the ability to process 300 containers through this pipe. This is a constrained pipe because you have no control over the freight ship. Obviously, the NHS doesn't pay you to hold a freight ship of your own, and even if you did, there's still only a certain amount of capacity in the dock. So you can so whatever happens, you could try and scale this portion by doubling the capacity, tripling it, whatever, but you'll still only ever be able to process 300 containers when it lands in the UK, regardless. So this idea of vertical scaling comes with a lot of problems, and this often means there's actually a limited capacity in our ability to deal with that. And this is one of the reasons why air freight from grounded planes was actually a major consideration when considering when trying to develop the dedicated PPE supply chain, because they had to basically bypass the shipping ports. They had to start using air freight, which then dropped it obviously into an airport, which was fine for the capacity at the time. But as soon as you've used up that capacity, you've still got a problem, because each of those planes has a limited capacity that is significantly less than 1 single freight ship. In fact, it might very well take about 200 to 300 planes to cover 1 single container ship. So that ability to scale your capacity actually is limited by the UK's ability to scale any of its port structure, which therefore is impossible. So that basically means that all the hospitals and all the pharmacies and all the GP surgeries are limited by the size of that pipe when it comes to anything that's manufactured internationally. You can see there's a series of problems here, and that's just on the capacity point. And never mind that we've talked about the energy, the CO2, and of course the disposal capability. I could talk about what we do in Automedi to then prevent some of this, given it has already come through this pipe, but what I want to do now is talk a little bit about why Automedi's scaling model is fundamentally different. So most of you who've been following our journey for a while will understand that Automedi's model is based upon what we call demand-side manufacturing. And demand-side manufacturing basically means it's not manufactured where the manufacturer can place the factory, but where people actually use the products. So we make it here. And if you think about what this means from the perspective of scaling, it means we have bypassed all this lot. Not required. And usually this composes between 70 and 80% of the entire carbon footprint of any product. So this number here, the total carbon footprint, 70 to 80% of it belongs in this part of the chain. Excuse me. There we go. The rest appearing here, typically. In some cases, it's more. But not only that, Automedi operates using very low power machines. So by comparison to the capacity of a factory, while each individual unit might have a higher carbon footprint, we cut out so much of this process, and we don't have a disposal footprint because everything is circular, that the net effect is a reduction of more than 96% in the carbon footprint of items that exist already. Right? So this is where we are. So what do we mean by demand side? So in our case, let's now draw a couple of pharmacies. Again, apologies for my terrible artist work. Right, so that's a pharmacy. And we have a GP surgery for the sake of argument. There we go. But there's more of these, isn't there? It's not just one. There are several. Let's copy that a few times over. Paste that in there. Perfect. Let's paste another one here for the sake of argument. So in each of these cases, they would normally be served, this cluster, this primary care cluster, if you like, each one of them will normally be served by one of these elements of logistics and supply. But again, that's limited by how much you can push through the UK's infrastructure, which of course was a problem during the early days of the pandemic. But here, we've now got the ability to stop that happening by giving them an Automedi machine. Within reason. What this now does is give each individual primary care cluster the ability to manage their own supplies by filling any missing pieces, if you like, with Automedi machines. So the net result of this is a fundamentally different scaling model, what we like to call horizontally scalable. So what does horizontal scalability mean compared to vertical? In vertical scaling, obviously, you have to scale every single part of this chain by making that capacity bigger. But as we've seen, you cannot do that with a UK port, and you are very unlikely to be able to do that with a freight ship, as well as any freight terminals. With our model, because all of that is immaterial, we have bypassed the constraint in the system. Our constraint now is different. And the constraint within an Automedi cluster is, I'll call it how many items or how fast you can get through this. But here's the catch. The beauty of our fractal style manufacturing networks is you create Automedi, I'll call it supplies within the PCN or within the CCG that, first of all, prevents stuff ending up in landfill because you're recycling the waste, but also you set it at an appropriate level that all your demand for the entire PCN or even the CCG potentially is covered by the Automedi circular economy. So that means you can take some waste, you can recycle it through a reclaimer, and that reclaimer may very well sit between two local networks. Let's put. So it could very well sit between the two if that's your demand profile. But each PCN may have one or more Automedi machines to their proverbial name. And what this then allows you to do is to scale that capacity both just in time, but also in a way that balances the supply requirements of the entire network as well as each individual part within it. So if you have a situation occurring where you need to get hands on, say, I don't know what would be good on tweezers for the sake of argument, every single GP can just ask their pharmacy or even have a machine of their own. And if you need more capacity, you simply get another machine because you don't have to duplicate the entirety of this chain above. You simply get another machine. And that's how you increase capacity. What does this give us? Well, as I said, it makes it really, really rapid to scale. You're just asking for another machine. Not only that, in a particular region, the machines themselves could be commandeered. Because if you're familiar with our product lines, we have a product called Quartic. And Quartic is our management dashboard, a bit like air traffic control, if you like. But the other thing it does is manages the jobs. And each of those jobs can be sent out to individual Automedi machines based on the demand required of it. So if there's a major incident, for example, in a particular area, all the Automedi machines located in that area can respond by Quartic sending them a job in parallel. And that means all of the items that are needed can be made in parallel and be almost instantly available at exactly the same time. So if we were to compare the two models with, say, a batch of 1 million items, what does a vertical scaling system allow us to do? The vertical scale in the old world, take that 1 million items, right, and you would have to send those through what would be, divide these two numbers out, it's around about the sort of 16 lorry loads. Right? And you can send those lorries as required to the freight terminal. It may very well be you might get one of them on the ship, you might get half of them on the ship. But in any event, you can't guarantee getting all of them on exactly the same ship to then arrive at the other end. And in any event, your 16 have got to be the 300 that the shipping port can then process, which you can never guarantee as well. In our case, we would typically deploy 50,000 Automedi machines into the community overall to serve exactly the same demand as that 1 million set of items. Quartic sends the jobs to all 50,000 machines. That means in a 1 million set, with this 50,000, each machine has to be able to produce 20. This cycle to here is typically no less than 3 weeks. Minimum. It's often 6 weeks. Quartic, on the other hand, allows you to distribute 20, or an order for 20 items, if you like, to all the Automedis around the UK at exactly the same time. And those 20 items might very well take 1 hour to produce in parallel. So all the machines are working at exactly the same time to print exactly the same thing. And then they're taken out by the people that need to use it, or the pharmacists nearby, and then delivered to where they're going to be used in a local area. And that means you could get an order of 1 million items going through 50,000 machines, each of them printing 20 at exactly the same time in one print job, and all of it will be ready within 1 hour. That's the power of horizontal scaling when you get it right, because there are no bottlenecks like this in our system. Everything is delivered digitally, and Quartic is potentially infinitely scalable and does it asynchronously. So 1 million, even 1 million jobs would be straightforward, never mind a small number like 50,000. So this is one of the reasons why Automedi is a fundamentally different proposition from the point of view of capacity and scaling. Because scaling Automedi in a horizontally scalable context creates this fractal network of networks, manufacturing network of networks, that allows you to operate in a decentralized manner. Not only that, when you need to, you can commandeer all of them to deliver the goods where they are needed. And this is a radical shift of manufacturing thinking more generally, because you never have to worry about running out of stock, basically. Send a job via Quartic, and it'll manufacture it where it's needed. This can be the hospital campus, where you have multiple Automedis, maybe 80 to 100 of them, or it might very well be several PCNs, where you've got 50,000 distributed across GP surgeries, pharmacies, physiotherapists, and council buildings. Everywhere becomes a circular economy. Everywhere becomes disposal. And it doesn't need any high capacity, high energy, large storage space. And crucially, there is very little waste. In these typical conventional systems, you have to stockpile to make sure that you can get your 1 million or so items through this pipe. So you've got to be providing capacity all the time through this part of the chain in order to keep topping up the stockpile to make sure that you have enough PPE. And as we saw, PPE expires. And that's one of the biggest risks, because you could be spending billions of pounds in this sort of infrastructure. While if you're producing stuff that through an Automedi chain, it's available with a very minimal amount of stock, maybe 5 for the sake of argument, 5 items literally in a PCN, right? But you have the capacity to produce as many as you need, and it be there where it will be used, removing the need for all of this logistics, the storage, and trunk logistics or haulage. If you have any questions on this, obviously drop me a note in the comments. Be happy enough to answer them. Okay, thanks very much, everybody. Have a great day. Bye now.